So today we're going to be talking about fugitive emission programs and specifically how, with changing regulations and new corporate goals around emissions and methane reduction, how we need more robust LDAR programs in order to meet those goals. So, how do LDAR programs, leak detection and repair, contribute to corporate goals? So, really, I think the first thing is we need to think of our LDAR programs as being an essential component of meeting those goals. Historically, LDAR programs have been focused on compliance. Much of the data is being collected and stored as part of record keeping requirements, but seldom is it analyzed to identify trends in terms of leak size, component types, or cross-referencing with other sites within the program. LDAR programs today are really evolving to be a really good quality data indicator of how facilities are being operated and maintained that can inform next steps in emission reduction programs. Instead of relying on gut instinct on where problems are, you can use technology to help you arrive at a data-driven set of solutions for the future. Further to that, there's evolving regulatory requirements. We're seeing this across industry verticals, whether it's oil and gas and landfills or renewable natural gas projects, along with those regulators are really looking at reducing methane through increased compliance. So, places like Alberta, the Alberta Energy Regulator requires a documented fugitive emission management program. And more recently in the EPA Quad O, B, and C rules, there's a requirement for a monitoring plan to be developed as well. I think that these programs don't really need to be complicated. You just kind of need to document, hey, here's our list of sites. This is the technology work practice we're being used, and here are our procedures to follow up on the collected data. But as we look today at some more complicated or more evolved LDAR programs, we really need some program management to help identify what we're trying to achieve. Thirdly, when it comes to LDAR programs and corporate goals, we need to be thinking about corporate risk mitigation. Environmental non-governmental organizations are performing aerial inspections using, planes and satellites, and they're publishing that data in publicly available databases. And showing up in those databases can be detrimental to your company's corporate reputation. So by identifying things more quickly, you can potentially mitigate them and lower the risk of getting caught. And then finally, really, when it comes to corporate goals too, there's a lot of momentum around verifiable methane intensities. Gas purchasers are really looking hard at the type of gas and the methane intensity of the gas that they are purchasing. And so a robust LDAR program can really keep more product in the pipe and provide useful data to help confirm that reported intensity. So to further drive this home, as operators are chasing further emissions reductions, LDAR programs must become more efficient. So this chart here is from the IEA showing the marginal abatement cost of methane emissions in the oil and gas industry, and it's kind of bucketed into three categories here. Things like reducing flaring and venting, setting technology standards. So that would be things like closed vent systems having zero emissions, or pneumatic valve performance, things like that. And then the third main category here is leak detection and repair programs. So the x-axis is the number of tons abated, and the y-axis is kind of the cost per million British thermal units in there. And so what we really want to drive home here is that, technology standards and installing flares or minimizing flaring is a big component of where we can find emissions reduction. But as we move into the long tail of what's available to us, really focusing on the LDAR programs highlighted in green here provide a lot of opportunity for not just oil and gas, but also RNG and landfill industries to improve their programs and really use an LDAR program as a way to build a competitive advantage. So what existing LDAR programs typically look like? I think the first thing is understanding that inspections are frequently independent of leak presence or size. So Most often when we're working with our customers, their kind of current mode of operation is something like what's shown here on the screen, where on the left-hand side of the screen, we're at the start of the year. At the right-hand side of the screen, we're at the end of the year. And in that year, there's a certain number of inspections that take place, typically with an OGI camera or a Method 21 instrument. And there's a time period in between. So this is a reactive workflow. There's no signal for us, for your LDAR technicians to go to site and look for these. It's very much, it's on a schedule. We're going to go look, see what we find. And this same process here is taken from each site with our 2 times a year OGI here, and it's just replicated completely across all of the assets. So this is regardless of the site characteristics like proximity to landowners, the size of the facility, the type of equipment present, or the amount of equipment present. So we're just doing the same thing at each site. And then finally, current LDAR programs are typically managed on a giant spreadsheet like this. Sometimes there's software, but more than often than not, it's in a spreadsheet with a schedule. And what we end up with is some summary information, some leak details, the facility it was found at, the detection date, the method used, where the leak was coming from. And then there's the opportunity to track repairs to closure in accordance with regulatory requirements. The challenge with these types of spreadsheet tracking is that there's a lot of free-form text inputs, so typos can make it difficult to cross-reference, even at site by site, like inspection to inspection. It can vary by LDAR technician, or it can vary across sites. You know, like the piece of equipment that might be identified as a pressure safety valve on your inlet separator at one site might be tagged differently than another site. So it's very difficult to generate some more advanced analytics. And in summary, like existing workflows are really just focusing on finding and fixing emissions that are occurring at the time. Another portion of current LDAR programs are the key performance indicators, or what we're tracking. And so these are some examples of some key performance indicators, or KPIs, that many companies are looking at. It's useful to break key performance indicators into leading and lagging indicators. To borrow a little bit from kind of more the safety world, leading indicators are proactive indicators, things we're doing voluntarily, like hazard identifications or near misses or other proactive inspections. More on the emission side, this would be our voluntary work. So deploying continuous monitoring for voluntary purposes, doing proactive OGI inspections just because we think there could be a problem there. Those would be our leading type of indicators, whereas lagging indicators are reactive. What did you find after something has happened? So in the safety community, this might be a spill or a release or a motor vehicle incident, and how we can then feed that back in to prevent them in the future. And on the emission side, I'd say lagging indicators are really getting into our compliance activities, performing AVOs, performing compliance-driven OGI inspections or Method 21. And really the key KPIs for existing LDAR programs are really just emphasizing compliance. And so we're going to get into how we can maybe enhance these by leveraging some technology later in this presentation. So what are the main challenges that we're dealing with existing LDAR programs? So there's 3 things here that we really want to focus on. The first is emissions vary temporally, which is a very fancy way of saying they vary through time. There's a large body of academic research that supports the idea that emissions are not persistent. Many are short-lived, many more are intermittent. So snapshot inspections often use some sort of engineering assumption on when leaks started to estimate total measured emissions from that LDAR program. Secondly, there's regulatory change coming across the industry verticals with which Cube works with. And typically those LDAR inspections are moving towards increasing the frequency of inspections. And so very obviously, increasing inspection frequency means we're going to need more resources to comply with the new rules. And so how can we identify that and potentially become more efficient? And then finally, one thing is there's not always clear alignment between LDAR workflows and corporate emission reduction goals. How do our LDAR programs really plug into the big picture of what we're trying to achieve? So looking at these more granularly, this is an example of how emissions vary through time. And what you see on the screen here is an example of about 5 to 7 days worth of continuous monitoring data collected from a cube system. The top time series here is the quantified emission rate in kilograms per hour with the red boxes and sawtooth line. And the bottom time series is the detected methane concentration at each device on site. So in a schedule-based OGI inspection, if we were to look at 3 different times here, at time A, we would estimate based on an OGI inspection performed on this date that the total emissions being emitted from the site could be in the 6 kilogram per hour range. If we were to show up at time B, we would get 0 kilograms an hour, and time C would be 2 kilograms an hour based on what's being detected. So these are all, it's not very consistent when we're looking at how emissions vary through time due to the temporal nature of these emission events. We really want a holistic view. And so when periodic inspections using an OGI camera or some other schedule-based detection yield wildly different results, how can we up-level this to get a better view of what's happening at these sites? Digging in a little more on inspection frequency, one thing that I think we found useful to think about is that when we're talking about one site, going from 2 inspections a year to 4, or in some cases 12, it doesn't seem like very much at one site. But when we think about all of the assets which our customers might be responsible for performing compliance work on, we start to see a very different picture in terms of the amount of effort that's involved to maintain compliance with existing workflows. And so what you see here on the chart on the left is 3 programs here. We have a biannual OGI program that's twice per year, a quarterly OGI program, which is 4 times per year, and a monthly OGI program, which is 12 times a year. And each of these colored bars represents the total number of inspections for each program based on the total site count. So the green bar is if your company has 10 sites, the red bar represents 50 sites, and the blue bar represents 100 sites. And so what we see here is that when we consider the amount of inspections we have to do, the amount of follow-ups that have to do to confirm that repairs have been made, as the inspection frequency goes up, the total inspection count goes up very, very linearly. And what this results in is if our existing field crews with our OGI cameras and trucks are at one level, as the inspection count goes up, those existing people are going to be at capacity. And as a result, we're going to have to expand our team of individuals, whether they're employees or contractors, in order to complete the required compliance work. And then finally, how do we plug in with our company commitments? And so here are some examples of some public statements that companies have made regarding methane and emissions reductions. You see a lot of themes in here about reducing of flaring, achieving corporate wide emissions or methane intensity goals, or conformance with international reporting frameworks. Things like flaring are largely addressed through, connecting pipes to the sites where flaring was being done continuously, or some other facility engineering work. A lot of those are low-hanging fruit, and that's why I think you see in here that up in the top right, that's a near-term goal by 2025. As we start to look at the long tail of how we're going to continually meet the rest of these targets over the medium term and long term, the LDAR program starts to become an important component. And one of the challenges with existing LDAR programs is they only have one lever to pull, more intermittent inspections. So if you want to continue to reduce your methane intensity, you have to inspect more, you have to find more things. And so your inspection count just continues to rise. So what does a new LDAR program look like where we can leverage technology and process? So the first component here is we really want to develop a program that helps align our corporate commitments to our LDAR program through program management. So it really starts with setting the right goals, um, defining the right metrics we're going to use to track. And then we want to leverage technology, get the right tools for the job to meet your goals within that program. We want to improve efficiency. We want to leverage data to inform decisions rather than going on gut instinct or brute force field inspections. We want to reduce that overall field work. And then finally, and probably most important, is we actually want to reduce our emissions, verify repairs, and achieve the goals of the program. So looking at our corporate commitments, we really need to start at the top. What are we trying to achieve? Some examples of goals companies are setting that Cube is working with might be things like reducing super emitters, reducing the time to detect and repair a leak, or just trying to understand long-term trends within their assets and see how facilities are performing relative to the expected emission rate, which could be from a permit or based on historical monitoring data. The next thing we want to do is define technology or deploy technology and work practice at the site based on the site characteristics. And so we're no longer just doing the same thing over and over again. We want to look and say, based on this site, based on the equipment here, based on the proximity to people, we might need a more beefed up program than some other smaller sites that are far away and can go to more of a by exception type workflow. Within this applying technology and work practice, this is where we want to start to leverage some software to help manage the process and automate certain tasks rather than just having a schedule on a spreadsheet. We're able to design a work practice that helps all stakeholders comply. Then we want to collect data, manage your emissions data, make sure you have the right data getting to the right stakeholders, and then move on to monitoring and measure emissions performance through time. What are those long-term trends looking like? Am I performing to expectations? And put that more into a continuous improvement cycle. And then if necessary, we want to have the procedures and work practice in place to respond to emissions based on the severity. So if we do have a large emission event, we can respond to it quickly and filter that into reporting. So really, this is more than a find and fix workflow. It's a continuous improvement management program. So as part of a new leak detection and repair program, we really want to get into what are the new key performance indicators that we can start to apply to the program that help us meet our goals. So in the black lines here are the same from the previous slide, thinking about our voluntary LDAR inspections and then our compliance work on the lagging side. But an LDAR program that has some technology support can also drive us to some new key performance indicators that might be useful for your company in meeting your goals. The first is really looking at technology-driven data. What are our month-over-month volumes, performing trend analysis, getting into equipment breakdowns, trying to really understand where the emissions are coming from through time. You can also up-level that even to the asset level, start comparing sites of similar vintage or similar type, and try and find kind of bad actors or good actors in there and try and bring that back to your engineering teams for continuous improvement. And then another key metric is really the time to detect. No longer are we solely relying on engineering estimates on when emissions started or stopped. We now have data streams that can help us really identify when something began, something ended, and how quick it took us to repair, if that's a goal for your organization. On the lagging side too, especially for our oil and gas customers, super emitters are a big deal. They want to really avoid those large events that are greater than 100 kilograms an hour in terms of quantified emission rate. And so we can really start to create some indicators around how many of those events we have, how many events of those do we have per site, and are we seeing them trend down through time? So for a new leak detection and repair program, we're not just emphasizing compliance activities, we're also introducing new performance metrics that align with corporate goals. So what does this look like? Here's our same sites that we had before, and new LDAR programs, especially with new regulatory rules, are allowing for greater flexibility in technology that can be deployed. It lets us consider the site type, the equipment type and counts, proximity to public, and the specific set of regulations that a site is regulated under. And so some sites might be very good to continue on an OGI program, with greater frequency. So you can see the 4 cameras here as opposed to the 2 that we had before. Whereas other sites, based on, our risk assessments and our analysis of the facility, might be better suited for a by exception workflow. And that's where deploying technology like Cube can help us only go to those sites when a response is warranted. Improving efficiency. So can we really get into the idea that technology-driven work practices can be more efficient than just scaling up our existing workflows? So this is a snippet from a simulation study that was done by Cardoso Saldana. He was at UT at the time. And what he did here is he ran a number of simulations comparing a continuous monitoring driven LDAR program versus a base OGI program. The image is a little busy, so I'm going to step you through this very slowly. On the y-axis here, we have the total number of labor hours for both inspections in the field, reporting, data input, things like that. And it's all normalized around 4 times OGI. And so what you see here on the y-axis is that 4 times OGI has a 1.0, a 2 times year OGI program would have a 0.5 because it's half the number of inspections. And then similarly, an OGI program that has a monthly frequency has 3 times the labor effort involved as the 4 times program. So we're looking here and saying this is the amount of labor we have to do when we're looking at the y-axis. On the x-axis, we're looking at the total emission reduction as a percentage. So again, it's normalized, but in this case, it's normalized to the do nothing scenario. And so the red line here in the middle is showing that a 4 times OGI program has about a little more than 50% reduction in total emissions, according to this simulation, compared to doing nothing. What we see here, though, these red dots, what they represent is various simulation runs. So there's multiple scenarios here being driven. And what we see here is that for a continuous monitoring driven program, according to this study, there's less field work involved. So in all of these simulation results, we were achieving the same labor, roughly the same labor requirements as 1 to 2 OGI visits a year. But we were also getting greater emission reductions compared to both the 4 times OGI program and the do nothing scenario, about 20 to 40% greater emission reduction. So what is this telling us is that a properly designed technology driven program can require less labor than an OGI program. Putting this more simply on the next slide here, if our current LDAR program has a certain amount of resources available to us, and they're all at capacity, assuming that everybody's running flat out for existing programs. If we were to look at new regulatory rules that are required, and we were to take that same program, we would have to expand our team. Alternatively, though, we can augment our existing team with technology to keep that team size the same and let our existing crews be more efficient at scale. This should be something that everybody should be interested in to keep our headcounts in line and still achieve what we're trying to achieve. So what does this look like very, very functionally? So in here, this is an example, a screenshot here of the Cube platform. And this is an example of an operator that was able to just reduce some emissions and verify the repairs. So it's a site in Canada where a Canadian oil and gas operator piloted Cube across several sites over a period of 6 months. And they were really interested in trying to develop alarm thresholds that would differentiate between normal venting processes, which are allowed in some jurisdictions in Canada, and identifying excess fugitive emissions. And so what ended up happening here is we, in conjunction with the operator, set some alarm thresholds that were at an appropriate level. So we were able to differentiate between what is normal venting and what is a fugitive, and then finally verify that once the repair had been made here, that we returned back to baseline. And so what you see here on the time series data of the quantified emission rate was no alarm was generated here. The vented emissions that were being detected didn't trigger that alarm threshold because these were allowed. However, when that rate creeps up here, and you can see how the red box is the magnitude of the red box here is very much higher than what we had during the normal venting. This generated an alarm that alerted the operator on site that a thief hatch had been stuck open. And then finally, once that thief hatch was closed again, we were able to see in the continuous monitoring data that emissions had returned to baseline and the thief hatch was closed. Another operator we worked with was really interested in reducing their super emitter exposure. So this was a large operator that was deployed cubes, continuous monitoring devices across 100 sites throughout the United States, and they had a specific goal to reduce large emission events. And so we set some alarm thresholds at an appropriate level, and the data from the cube system was integrated with operations work practices. And then following a 12-month period, we did a review and tried to assess their performance. And so what we see here is that over a 12-month period, the total volume detected at these sites was reduced by about 90%. Most of this is the work the operator was doing using the continuous monitoring data to identify issues they were having in their operation. So things like taking equipment that was out of service, disconnecting it from the main process, making some upgrades to flare and closed vent systems. But as interesting as this is, the other key piece here was reducing those large emission events. And so those super emitter scale events in that 100 kilogram an hour level went from 100 in the first month down to 10 at the end of the study. So this was a success here in aligning with that goal of reducing large emission events. And then an example of trending and reporting, looking at long-term example of data. So an operator had deployed some Q devices across some US oil and gas assets. And originally they were very much interested in just getting some alarms and responding to those effectively. But after 6 months, we wanted to do a bit of a look back and look at where the detected emissions were coming from certain equipment groups or equipment components themselves. And what we found was two things working with the operator in this instance. First was that the heater treaters on site, the burners, were exhibiting some evidence of incomplete combustion, where we correlated the methane and carbon monoxide data streams to identify incomplete combustion in those pieces of fired equipment. And also that the tanks were found to have persistent emissions during trucking operations. And so the operator did two things. The first was they identified burners that needed to be tuned, and they got a burner technician out there to lean out the burners. And then the second thing that they implemented was asking truckers to maintain a minimum fluid level when hauling from site, rather than sucking them dry and pulling those thief hatches open. And the results ended up here is that when we looked at our heater treaters and our tank emissions, we see a substantial reduction over the 12-month period, averaging about to 80% for both equipment types. So this is an example of using long-term trending of continuous monitoring data to help identify further ways to reduce emissions within your operation. And then finally, this is an example of a cube deployment at a renewable natural gas facility where methane is being captured from an agricultural operation. So in here, an operator was very much interested in just finding leaks more quickly than their conventional leak detection practices. For RNG operators, reducing time to repair is a very important metric. It's very economic for them to fix these quickly due to some low carbon fuel standard credits that they receive selling gas in certain jurisdictions. And so in this case, an alarm was generated by the Cube system as soon as the emission rate exceeded the threshold. And ultimately, the operator was able to go to site and repair here. And in this instance, the time to repair was reduced from days or weeks into about 24 hours, which is a very positive result for this particular operator. So wrapping up here, just for trying to build a new leak detection and repair program, there's kind of 4 things that we need to go through in order to implement one of these programs. So the very first one, like we were talking about, is defining what you're trying to achieve within your program. What are your main goals? Are you looking for just getting early notification of emissions that are abnormal? Are you trying to avoid large super emitter scale events? Or are you trying to really home in on those long-term trends? Those are all admirable goals and will work. We want to make sure to engage stakeholders early and often. We've seen most companies be successful when they have operators, air quality experts, facility engineers, and management and executive all at the table, kind of defining what they're trying to achieve and how they're going to achieve it. Then you want to get into testing and deploying technology. One of the key considerations here, especially if you're deploying technology for the first time, is you want to be thinking about getting collecting enough data to make a significant decision about the best way to approach the program go forward. Often data from one site is not enough. That could be an outlier for the better or worse. And so by thinking about how many sites you have total in your operation and picking a fairly large percentage of those sites, could be in that 10 to 20% range, that'll help you make a best decision on how this might look at scale and give you a very good idea of what a scaled up program might look like. And then once you've seen how the technology is performing and how your work practices are performing, that's where you can really start to implement that new program at scale. So what does it look like getting started with Cube? In case you're wondering, our internal engineering teams and our partners can help you understand how Cube's continuous monitoring technology can plug into your existing programs, whether you're seasoned veteran with methane technologies or you're just getting started. We can advise on work practices, helping you set alarm thresholds, and designing programs to test regulatory-driven work practices, and then help you, track the effectiveness and design some reporting to support specific workflows. So whether you're just looking to avoid the big releases or you're looking to confirm your methane intensity, Cube has experience working across oil and gas, RNG, landfills, and mining use cases around these items. To deploy with Cube is really easy. It takes us all of 5 minutes to generate a deployment plan. All we need is the lat-long coordinates of the site. And what we do is we use prevailing wind direction from a nearby wind source, whether it's an airport or a nearby site with some Cube data on it. We identify the sources, and based on that prevailing wind direction, we kind of optimize the device placement here shown in the black circles. That'll give the best balance between source coverage across the site and minimizing cost for you as the end user. And then once you're up and running with Cube, there's a lot of data here that's available to you. We do deliver time series data down to 1 minute increments in terms of quantified site rate. We have the ability to integrate with third-party data, whether it's external from Cube via API or pulling in data from things like OGI surveys or other inspection data. We do have some additional visualizations where you can overlay plume simulations to see how a plume moves through time, as well as provide some out-of-the-box data on breakdowns by equipment category and source. And then finally, tracking of alarms all the way to closure. So if an emission event detected does exceed the threshold, you'll receive a notification from the Cube system and can action your teams to respond in a timely manner. That's all I had today. Thank you very much for your time. Again, I'm Andrew Walsh. Feel free to get in touch with me if you have any questions, and